What's up, robots? What are we talking about today? Oh yeah, elastic and inelastic collisions. Duh. It's written right there on the board. Can't you see it? Um, so this is potentially the last lesson in the unit, but you know how it goes. We might do one more. I can't quite decide yet. I feel like there's something missing, but I can't put my finger on what it is. Um, Mr. Barton, don't you just have a list of stuff we're supposed to learn? Well, yeah, there is a list, but that list sometimes it lies. You know what I mean? Sometimes it it tells me to teach you stuff that's totally whack and you don't need to really know it. And then other times it doesn't tell me to teach you stuff that I think is really neat. And then I want to teach it to you anyway. So I can't decide if I'm missing something that I think is neat or you know what I mean? I don't know. Oh well. I don't know. We'll figure it out. If you feel like you're not learning something, let me know. If you don't know something, let me know, right? It's like how do you know that you don't know? But anyway, we're getting off track here. We're going to talk about elastic and inelastic collisions. They're going to be tight and they're going to be real loosey goosey because we are dangerously close to just an obscenely egregious amount of mathematics. Um, I wrote a problem today and then I erased the problem because I realized that the problem was gonna be 5 seconds of physics and then 20 minutes of beating this thing to death with systems of equations. Which, I mean, don't get me wrong. I love to beat a problem to death with a system of equations. But I know you guys don't. And to be quite frank, neither does the AP test. So it just doesn't make a lot of sense. You know what I mean? Like if you're not having fun, then like why are you even here? You know, you feel me? I mean, you're here because it's a state requirement. It's just anyway. All right, for real, for real. Let's learn. Okay, definitions. So for the whole universe, collisions fit into kind of two categories, maybe like two and a half categories. So those two categories are, and of course my pen's not a pen. Why is my pen not a pen? Now it's a pen. Okay. There are two categories, and those two categories are elastic collisions and inelastic collisions, which is like saying collisions and not collisions, right? Like these things and the opposite of these things. It seems like you could do that with a lot of different categorizations, but let's talk about them. Elastic collisions are when two or more objects interact via a conservative force. Conservative forces are forces that you associate with conserving energy. These are forces like springs, gravity, pretty much those two. There are other conservative things out there, but the test for conservativeness is kind of a janky. It's a test that we don't want to get into. Um, so pretty much it's gravity and springs. So when two objects interact via a conservative force, here's the important bit: the momentum is conserved, which is true 100% of the time, and mechanical energy is conserved, which is not true 100% of the time. So let's maybe talk about why this is. I always, or maybe not always, but it kind of dawned on me that this is a weird thing, right? Why is momentum conserved 100% of the time and energy isn't? Mechanical energy? Um, it's a weird question, right? It's something that I feel like I haven't thought enough about to give you a proper answer yet. But it's an interesting question. So we'll talk about kind of where does that mechanical energy go when it's not conserved. But then we'll mostly focus on momentum because we're in the momentum unit. But anyway, so elastic collisions, the important bit, momentum's conserved, so is mechanical energy. Okay. Inelastic collisions are when two or more objects interact with a non-conservative force, which is pretty much every force that isn't gravity or springs. I think there's a few others out there that are conservative forces, but they're a little out of our wheelhouse for right now. Okay. And momentum is conserved, but mechanical energy is not conserved. So don't think of this as like a binary thing, right? It's not elastic or inelastic, right? There are what are called perfectly elastic collisions where 100% of the kinetic energy is conserved. Okay? And I think the AP test might be using these two phrases synonymously or interchangeably. They might say, an elastic collision conserves it 100%. And then there's not perfectly elastic. But I mean, there are things that it's kind of a spectrum, right? Think, for example, bouncy balls. Those things bounce, but when you bounce them, they don't come back up to 100% of their initial height, right? Like when you bounce a ball, it starts here and then it goes like this, right? And it gets lower and lower each time. And the better the bouncy ball, the closer to this max height it comes back, right? Whereas if you drop like your sock, it doesn't bounce at all. It like hits the ground and then it lays there. So there's like a spectrum. Okay. It could go all the way back up to the top. 100% of the gravitational potential energy comes back when it bounces, or literally none of it does, and the sock just hits the ground and stays there, like a wet sock, even. So there's definitely a spectrum to it. You could have like partially elastic where it bounces, but you don't get 100% of that energy back. In real life, in practice, you're not really gonna find a perfectly elastic collision. Because if two things touch, there's gonna be some rubbing and deformation of the surfaces going on there. So really the only perfectly elastic collisions happen with like gravity slinging stuff around and maybe like protons and neutrons slinging each other around, stuff like that. And they're not even really colliding. They're just kind of like being pulled on by each other and interacting through a force, but they're not running into each other and bouncing. So keep it in mind. Okay, so let's give you maybe a more intuitive idea about what we're talking about here. So for elastic collisions, it's exactly what it sounds like. Elastic means we have a springy thing, and I'll leave that up to your imagination, that bends and flexes, storing energy. This shouldn't say they. This should say then unbends and recoils back to a resting shape, restoring or returning that stored elastic energy back into kinetic energy. So if something bouncy or flexible runs into something, bends, and then bounces off, we're probably looking at an elastic collision. Okay. Will it be perfectly elastic? Almost nothing in real life is. But it'll be pretty elastic. This would be like if you have something with a spring on the end running into something else, like a pogo stick, that would probably be an elastic collision. If you have two things tied together with a bungee cord, that would probably be an elastic thing going on there. If you have some kind of like flexible rubber in between them and they bounce off each other, that's probably elastic. Okay. Inelastic is quite literally the opposite. It's anything with just buttloads. Sorry, am I allowed to say buttloads? Bottom loads of not flex and bend. Um, anything that's real malleable and like doesn't retain shape well, like water. Water is not elastic. Socks, stretchy. So if you stretch them, maybe, but they don't bounce, right? So anything that's not flexible or bendy, anything that's less malleable, the less energy is going to return from the collision. The like most antithetical, hopefully that's a word, just like it was hopefully a word last time, would be like if you took a wad of silly putty and then you threw it at something, it just like splatters all over and sticks to it. That's like the most opposite of an elastic collision that I can possibly think of. So we're going to look at some examples today where things stick together. If things stick together like silly putty sticks to stuff, you're looking at an inelastic collision. It's literally impossible for things to stick together and be elastic. Because if you're sticking together, you're gonna compress a spring, and then you're never gonna uncompress it and get the kinetic energy back out. So I think maybe we should amend this a little bit. It's not necessarily that that the mechanical energy is conserved, because we could squish a spring in between things and store energy in the spring. But the point is, it has to bounce back off and release that, and the kinetic, come on, the kinetic energy before and after the collision have to be the same. Okay. So now that we've really beaten that to death, let's talk about one more idea, and then we'll dive into some examples to try and hammer out these ideas. Let's talk about our center of mass. This is a thing that we could spend a lot of time calculating and fighting math with, but I'm going to try and give you kind of an idea of what it is and how you would find it. And then I'm going to give you a principle we can use for collisions, and then we're never going to calculate it again. Actually, I don't want to say never, but you get the idea. So the center of mass is exactly what it sounds like. It is the center of the mass, right? And right, just because I put the word the in there doesn't make that any more like obvious, right? But what it is it's a weighted average of the location of the mass. So let me maybe give you an example. If you have two masses, you have a ball here and a ball here, and they're the same mass, they're the same size. The center of mass is right in the center of them. Okay. Here's the weighted average part of it. If this mass were twice as big as this mass, then this center of mass is going to move slightly closer to the center here than this one, because there's more mass over here, right? And then if we take this kind of to the extreme, like the center of mass between like a human and the Earth, here's the center of the Earth. The center of mass would be like there, because most of the mass is inside the Earth, right? So the weighted average part means that it's more towards where most of the mass is. For uniform objects like spheres and boxes, their center of mass, not like the center of mass of this two ball system, the center of mass of this object is generally in the center of the object, unless you have like varying densities. like if you've got think like a water bottle, and then but the water bottle has like I don't know, you put something in it, like you put like you got water in like the bottom, right? Just the bottom. Then the center of mass is probably closer to down there because water's a lot heavier than this plastic shell. So you get what I mean, though. It's the center of where most of the mass is. Okay. It can be inside of an object like these, or it can be floating out in space, not connected to any physical thing. The center of mass is like a mathematical object. It's not a real thing, it's a location. And so location where you're exactly evenly pulled on by all the gravity around you or something like that, right? We don't want to get too formal here because it's high school. It's not that serious. Okay. But there's what center of mass kind of intuitively is. Here's the principle that you need to know to do problems with. The center of mass, the velocity of the center of mass does not change in a closed system. Okay, what that means, let's say we've got a little object and it's going to come hit this stationary big object. Actually, let's not say that. Let's say it's going to hit this object. Okay. Let's plot the center of masses. Okay, the center is right about there. So that's the center of mass. This object is moving. So then it moves halfway closer. Okay. Now our center of mass is halfway between these. It's about there. It moves the same distance again. Now our center of mass is about there. It moves the same distance again. Now our center of mass is about there. It hits this thing. This one stops, and this one will move. Our center of mass is right there. This distance, I didn't draw it very well, should be the same every time. The center of mass, before and after the collision, should be going the same distance every single time. Right? So maybe if I already put them out, I could do it a little better, right? So center of mass is here. It goes to there. It's there. It goes to there. It would be there. It goes and touches it. This one goes there. You get what I mean. The center of mass, if you graph it with a collision, this thing's coming in, constant velocity, boink. This thing comes out, and the center of mass will not even change a tiny bit. Okay. I wish I had slightly better like animation skills so that I could show you this. But I don't. You know what I mean? It's a shortcoming of mine. It's something that I don't know. Maybe someday I'll be a better person, but not today. Maybe tomorrow. But anyway, center of mass does not change velocities during collisions. It does not change in a closed system. We're going to use that to our advantage later. Okay. Basically, memorize that fact. I've seen like 3 AP questions that say, what happens to the center of mass when these things bump into each other? And the answer is always, they don't change. Okay. The only way you're going to change the velocity of the center of mass is if you interact with something that's an open system. And like we talked about in the last set of notes, that would be like you run into an immovable object, like you bounce a ball off a wall. Okay, obviously that's going to not be a closed system because you don't want to include the whole wall and the whole earth in your system because then it's too hard to measure. So you're just like, screw it. It's an open system. There's an impulse and momentum changes. Okay. In an open system, velocity of your center of mass can change. But in a closed system, it's just going to keep on keeping on forever. All right. Let's do some problems and then talk about some stuff, and then you can go do some practice problems, and then you can see how much you actually learned. Hopefully it's a lot. So let's start with this. A dart of mass m, so all right, little m here, is thrown at a block of mass capital M, hanging from a very light string. The dart is moving horizontally with a speed v. Okay, so this thing's zooming. Velocity initial equals v. Immediately before it hits the block, the dart embeds itself in the block, and both of them swing up to a height h. So from here to wherever the center of mass is, probably like there-ish, this height is h. Would the block dart system experience an elastic or inelastic collision? Which object, the dart or the block, would experience a greater magnitude of impulse? Okay. So let's answer the first question first. Would it be an elastic or inelastic collision? Because we have an object sticking to another object, this is an inelastic collision. Okay. For it to be elastic, this dart would have to have like a spring on the tip, and then when it hits this mass, the mass would have to swing up, and then the dart would have to bounce off, right? Or maybe the other way that I've seen a similar problem is you have your block, and instead of shooting a dart at it that sticks in this thing, they shoot a rubber bullet at it. So this swings up, and then the bullet bounces back off and goes the opposite direction. You need something rubbery and bouncy. If it bounces, it's elastic. If it sticks, it's inelastic. Okay. So this is an inelastic collision because we have two things sticking together. We're going to look at a lot of inelastic stuff today because honestly, most things in real life are inelastic. Okay. Which object, the dart or the block, would experience a greater magnitude of impulse? Okay, so let's talk about impulse. Impulse is our change in momentum. So let's investigate the changes in momentum here. This dart has some momentum coming in. Let's look at our initial and final momentum, shall we? So we're going to look at right before the dart hits and then right after the dart hits. So let's reset this back to starting. Let's get rid of some of this doodling that I've got here. There we go. Okay. So initially, our initial momentum is going to be whatever the mass of the dart is, m, times the initial velocity of the dart, v. Okay. No matter what, not no matter what, in a closed system, so our system will be dart plus block. Okay, now it's a closed system. Momentum will be conserved. So we can say that this will equal our final momentum. After the dart hits the block, they're going to travel together like so. So if they're stuck together, they have to have the same velocity. So our new momentum is going to be the velocity of the whole system. We'll make it maybe a bigger V, capital V. And then the mass here would be the combined mass. The mass of the dart. Sorry, we don't need that. Plus the mass of the block. Okay. So they're going to be equal. Here, our dart, if it hits this thing, it's going to slow down. Our dart is going to lose momentum. However, our block is going to get hit by a dart. It went from not moving to swinging upwards. is going to gain momentum. However much momentum this dart loses, this block will gain. So the change in momentum of the dart, however much it loses, will be equal but negative, right? This one's going to lose, so it's going to go down. It'll be a negative value. Here, it will gain momentum of the block. However, the magnitude is the absolute value. We just care about the size of this. They'll be equal. So the impulse that the dart feels and that the block feels will be the same size, opposite direction, because the force from the block will be that way on the dart. The force from the dart on the block will be that way. Okay, cool. So same size, different direction. Magnitudes will be equal. Okay. If you really want, you could make up masses for this, right? If you're like, Barton, you're not really showing me how to do the physics, right? Pick some masses, right? Like here's a dart. How big are darts? I don't know. The mass of the dart equals 100 grams. The mass of the block, make it as big as you want. I don't care. Capital M is 2 kilograms. And then make this thing go as fast as you want. This V initial equals, screw it, make it 50 meters per second. Throw that thing at like 100 miles an hour. You know what I mean? And then see if you can do the problem. See how high this thing would swing. So yeah, you could do it if you feel like it, right? This is left as an exercise for the viewer. That joke's a lot funnier to me than it probably is to you, but I've got years of trauma from college, but I digress again. Anyway, it's inelastic because they stick together. They're equal because momentum's conserved. Next slide. Okay. Let's talk about finding a center of mass velocity. This is kind of fun. So we have two carts of identical masses. So they're both mass m. Okay. One is moving at 2 meters per second to the right, and the other is moving to the right at 4 meters per second, such that the faster cart is approaching the slower cart. You're approaching me? I hope you guys get that joke. Okay. So this one is going 4 meters per second that way. This one's going 2 meters per second that way. So they're going to eventually run into each other, right? This one, if we put like a little scale here, we got 1, 2, 3, 5, 7, 8, 9. Okay, so this one will go 2, 1, 2. This one will go 4. 1, 2, 3, 4. They collide. Now they're gonna bounce off, right? So this one will get a little bump and speed up. This one will get a little bump the other way and slow down, maybe stop, maybe turn around. Let's read the rest of the question. The cart has Velcro. Did you know that Velcro is like a company? The same way Band-Aids are adhesive bandages. Band-Aid is a brand. Adhesive bandage is the item. Velcro is the brand. It is a hook and loop strip or something like that. I don't know, but Velcro, right? They have Velcro on them, so they're gonna stick together. Okay. What is the velocity of the center of mass before the collision? So let's look at this problem. And what we're gonna do is we're gonna do some math because honestly, I'm just jonesing for it and I can't avoid it anymore. We gotta do some math. Okay. So V initial here is 4 meters per second. V initial here is 2 meters per second. This one catches up, bumps into the back one. They stick together, and then they're going to move to the right. Because they're an equal mass, you can probably guess how fast they go after they stick. But let's do the math, not the mass, the math just to figure it out. So initial momentum is equal to the momentum of cart 1. So we don't know their masses. They're identical. Let's call them M. So it's going to be M times velocity of 4 plus the momentum, this is momentum 1, momentum 2, is going to be the same mass because it's the same size, times velocity of 2. So we have a total momentum of 6 times the mass of the carts. Okay. This, because it's a closed system, that's my system, the 2 carts, they stick together. This is going to equal the final momentum. They're stuck together. So what's the total mass at the end? 2m for the mass. And we're looking for the final velocity. And you're going to say, why? We'll get there in a second. So we can divide both sides by 2m. The m's cancel. 6 divided by 2 is 3. So our final velocity is 3 meters per second. Okay. Which makes sense. That's the average of these two, right? This one slows down a little. This one speeds up a little. They meet in the middle right at 3. Okay. If the masses were not identical, then it wouldn't be right in the middle. If this one would be bigger, it'd be closer to 2. If this one was bigger, it'd be closer to 4. Okay. So now, how does this help us find the velocity of the center of the mass before the collision? Well, going back to my original ramblings, the velocity of the center of mass is constant before and after the collision. So if after the collision, let's move these. After the collision, these things are stuck together and they're moving like this at 3 meters per second. The center of mass is right there. And this location, this thing, this spot is moving that way at 3 meters per second. If it doesn't change during a collision and it's going 3 meters per second after the collision, it was going 3 meters per second before the collision too. So the answer is 3 meters per second. Cool. That's tight. Again, if I were a better animator or something, I would now have a sweet like GIF or something for you to look at. Maybe next year. All right. Last example, and we're going to look at explosions because we got to look at explosions. And then we'll get you on your way. So a slow motion camera is pointed at a small explosive that's suspended by a very light string some distance above the ground. So we've got like a rack, string, explosive. Okay. The explosive is detonated and breaks into 3 distinct pieces of roughly equal mass. Ooh, look at that. Already 3 equal pieces. Oh no, except now it's broken. Okay, all right. As intended. They designed it that way. The footage from the slow motion camera shows one piece of the explosive moving horizontally to the right with a speed of v. So let's pick this piece. This piece is going to explode and it's going to go that way with a velocity of v. Let's make that maybe a velocity of v. Okay. Another piece is moving vertically with a speed of 2v. So this one somehow got pulled and is going straight up with a speed of 2v. What is the horizontal and vertical components of the velocity of the third piece that could not be seen on the footage? So there's an explosion and we couldn't see this piece here. It was hidden by the smoke and the flames and all that stuff. We didn't see it on camera. How fast was it going and what direction, right? Okay, so let's break this back down. Initially, before the explosion happens, our bomb is just sitting there. So the initial momentum is 0. Okay, cool. So now, this piece flies to the right at V. This piece flies up at V. So momentum is a vector. Like all other vectors, you can break it into components, a vertical component and a horizontal component. It must be conserved in both directions. So the initial momentum in the x direction was 0. The initial momentum in the y direction was also 0. Okay, so now that means our final momentums in the x and in the y directions must also be 0. So let's look at it. This piece here, it has some mass. It's got a mass of m, and it's going a speed capital V. Okay. This mass is going vertically, so we'll put it on the y equation, has a mass of m, and it's going a speed of 2v. What is this one doing? Okay, well, it has a mass of m. It's a third roughly equal mass. Okay, so it's going to be m, just like the other two. Its velocities need to be in a way that cancel the momentum from this piece and the momentum of this piece so that the total is still 0. If we had 0 at the beginning, we need 0 at the end. So for it to cancel the momentum of this piece, it needs to have mv momentum, but in the opposite direction. So it has negative. So actually, let's look at it. It has m negative v because the direction comes from the velocity. It needs to be going just as fast as this piece horizontally so that its momentum in the x direction cancels the momentum of this in the x direction. Now, this piece is going up at 2v, so this piece needs to be going down plus m times negative 2v. So this piece is going to the left at negative v and down at negative 2v. So its total velocity is this. It has a horizontal component of v, a vertical component of 2v. And then if you wanted to find this, we could, using Pythagorean theorem, right? V squared plus 2v squared equals, so vx, vy squared equals v squared. So we have 2 squared is 4. We have 1 plus 4 v squared. We have 5 v squared equals v squared. Square root. So it's going whatever the square root of 5 is. What is it, like 2.2 something? It's going like 2.2-ish meters per second that way. More down than up. So, all right. Hopefully this helped. Hopefully this taught you something. Hopefully you're okay on the homework. I think there is one with some data and some graphs. And I know we didn't really talk about data or graphs today. But if they're asking you to conserve momentum, just look at, like, what is the momentum? I think they give you enough information to just straight up calculate momentum, right? Even if it's in terms of like m times a number, they might not tell you mass, but they'll probably tell you the velocity. If they ask you, is the kinetic energy conserved? They have to tell you some velocities. And just remember that your kinetic energy is 1/2 mv squared, and then you should be fine. Okay? If you get stuck, we can always go over it in class later. As always, I hope you learned something. If not, go pound sand. I don't know. Sorry, it's a free education. What do you want? Anyway, I appreciate you guys. Have a good rest of your day. Let me know if I can help you with anything. Like and subscribe. I'll see you guys next time.